In part one, we talked about how to find the derivative by estimating the slope of a tangent line on a graph. Now then we talked about how to find the derivative numerically by picking a point really close to the point of tangency and finding the slope of that line, and finding the slope as the x value got closer and closer to 2 in this case that we were looking at, this example that we're looking at. So we've actually been looking at this slope. This is just a slope. This is f of x minus f of 2 over x minus 2. And this is the slope between the points 2, 20 and f of x. And 20 is just f of 2. That is the value of the function when x is 2. So this is just another way of writing the slope. This is y2 minus y1 over x2 minus x1. Now, if we were to plug the number 2, substitute the number 2 into this slope formula, we would have f of 2, or 20, minus f of 2, so 20 minus 20 over 2 minus 2, which would give us 0 over 0. So this is not defined. And that makes sense because I can't find the slope between 2 points that are the same point, because my numerator and denominator will both be 0. But because of the fact that that is a 0 over 0, that is a removable discontinuity. That corresponds to a hole in the graph when we did a rational function. It was removable. I could fix it and find the limit. So this is what I'm going to do with this particular function. Now, we know from above that f of x was equal to x cubed minus, I'm going to have to look now, x cubed minus 13x squared plus 52x minus 40. So what I'm going to do is I'm going to substitute this value for the function in for f of x. So all of this is going to be substituted in for f of x. And 20 is going to be substituted in for f of 2 because 20 is equal to f of 2. So I'm going to rewrite my limit like this. The limit as x goes to 2 of x cubed minus 13x squared plus 52x. And you know what? I want to do this in red so it's really clear exactly what I'm substituting. X cubed minus 13x squared plus 52x minus 40, and then the f of 2 minus 20. So f of 1 x, or y1 minus y2 is the function, the whole function with just some generic x in it, minus 20, all over x minus 2. And if I combine those two constant terms in what I've just written, I'd have x cubed minus 13x squared plus 5x minus 60 all over x minus 2. And if I substitute 2 into the function, I end up with 8 minus 13 times 4 plus 10 minus 60. Oh, that's supposed to be 52x, not 5x. I knew that looked wrong. Many of you are probably screaming half point by now. Okay, plus 52 times 2 minus 60, all over 2 minus 2. And if you compute everything in the numerator, you have 8 minus 52 plus 104 minus 60. It turns out to be 0. So you end up with 0 over 0, which is what we expected because we had 0 over 0 already figured out from up here. So what I need to do whenever I have a removable discontinuity is I need to rewrite my limit in factored form so I can get rid of that discontinuity, that troublesome factor. So since 2 is a 0 of both the numerator and the denominator, I know that my numerator has a factor of x minus 2. So it has that factor, and then it has some quadratic factor as well, because it's an x cubed altogether. So if I factor an x out, then I would have an x squared here. In order to figure out what that missing factor is, I'm going to do some synthetic division. So putting 2 in here, and I have 1, negative 13, 52, and negative 60. Notice my numerator has a constant of negative 60, not negative 40, because those two combine together to give me the numerator of my slope formula, because my slope is this minus that. The red, what's in red minus what's in blue. Doing synthetic division, this becomes 2, negative 11, negative 22, 30, 60, and I get 0 remainder. And I should get a 0 remainder. If you do not get a 0 remainder, you've done something wrong, because I already know that 2 is a 0 of my numerator. This becomes then x squared minus 11x plus 30. Now I can cancel out my discontinuity, plug the 2 into the function. So basically now I'm taking the limit as x goes to 2 of x squared minus 11x plus 30. Plugging that number in, I get 4 minus 22 plus 30, which is equal to 12. And 12, isn't 12 what I thought my limit was, or my slope was appearing to approach 12? So when I get my limit as equaling 12, I am very happy, 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 because that's what I expected it to be. Now you might think, well, what's the point of going through all that when I was pretty sure it was 12 anyway? Well, this happened to be a nice number. You might get a derivative where the number isn't as nice, and so you need to know exactly what it is using this method. So this is finding the derivative algebraically using limits.